What's up, guys? Welcome in. This is going to be the first lesson for Unit 3. If you haven't met me yet, my name is Coach Perkins. I also teach Algebra 1 um, at Keller High School. If you have not met me yet, you can always stop by my room and talk to me about anything. But today we're going to get started with the first lesson of Unit 3, Slope and Rate of Change. You've probably talked about some of these things in the past, but we're going to dive in a little bit deeper to them, make sure we fully understand them before we get into the super fun stuff like graphing. Okay, so to start it off, right, we have slope. Slope is the ratio of change in the y-coordinate, aka the rise, to the change in the x-coordinate, aka the run, okay, as you move from one point to another. The key concepts of this lesson is going to be that the slope can be used to describe a rate of change. Okay, and you'll hear us talk about that over and over and over again. And then also, it's going to describe how steep a line is. Okay, so it's going to be talking about rate of change, and then if we're looking at a graph, how steep a line is. The slope, right, is non-vertical line that is a ratio that is rise to run. You've also might have heard of it as rise over run, right? Rise over run. Okay. And you've also probably heard of it as the variable m. Okay. And then we're going to use this formula down here, right? So this is super, super, super important, right? This is the slope formula is y2 minus y1 over x2 minus x1. The reason why we talk about that is you can find slope using rise over run if you're looking at a graph, and then we'll talk about other ways to do it. But this method always works, right? So the slope formula is our go-to, always works method, and we'll talk about it probably on each and every slide. Okay, the rate of change is a ratio that describes, on average, how much one quantity changes in respect to another quantity. And mostly that's talking about your change in x and your change in y and how that relates to each other. To go back to last unit, right, if x is the independent variable and y is the dependent variable, then your rate of change is going to be your change in y over your change in x, right? And you see these little triangles. Technically, that's delta y over delta x, but we would just say it by the change in y over the change in x, okay? And it's always, always, always y over x. The number one mistake we see, especially on this unit, is flip-flopping the y and the x and doing x over y. We want to always do the change in our y over the change in our x. Okay, so some examples. We're going to find the slope given 2 points, a table, and then also we'll eventually talk about a graph as well. When I'm given 2 points, I want to use the slope formula. So the slope formula is y2 minus y1 over x2 minus x1, and you might be thinking, Coach Perkins, that doesn't make any sense. What's x1, what's y1? They just give you points, okay? So remember, points are just given to us as x comma y, okay? And so what I would suggest you do anytime they give you 2 points is go ahead and label each one, right? So if this is an x and a y and an x and a y, okay, I would just label this first one, okay, that's my x1 and my y1, because that's my first point. Then I've got my x2 and my y2. Okay, from there, you're just plugging these values into our slope formula that we talked about a second ago, right? So if I'm looking at y2, well, my y2 value is this 5. So I'll have 5 minus y1, so it's always minus, and then y1 is 0. So 5 minus 0 over x2, which is 1, minus x1. My x1 is negative 2, so I have to do minus negative 2. Okay. So looking here, that top is super, super simple to solve, right? 5 minus 0 is 5. Okay, that bottom part, right? 1 minus negative 2. Okay, 1 minus negative 2. Anytime you're minus a negative, right? It's kind of like the distributive property where we have to distribute this negative to what's on the inside, right? And a negative times a negative gives you a positive. So it's really 1 plus 2, which would give me 3. And that would be my slope for this line. Go ahead and leave your slope in fraction form. Okay, so don't try to turn this into a decimal for two main reasons. One, it's an extra step. It's just completely unnecessary. And two, once we get to graphing, it's actually going to be way more beneficial to have this already written as a fraction because we're going to eventually do rise over run for our slope. And to do that, we need to have it set up in fraction form. It's going to be really, really difficult to like do rise over run with like 2.67, right? That doesn't make a ton of sense. Whereas if you had the fraction form, that would work too. Okay, on this second example, okay, they give you a table. There's two main ways we could do it, okay? We could use the slope formula as well, right? If we've got x1 and x2 and y1 and y2. Or on a table, it's a little bit simpler, right? If I look at my change from negative 3 to 2, I got to think, okay, how much did that increase or decrease? From negative 3 to 2, that went up 5, so plus 5. Okay, then I got to do the same thing for my y value. Okay, from 4 to negative 3, that went down 7. Okay, so minus 7. And then the key thing to remember there, it's our change in y over our change in x. Okay, what was my change in y? Was negative 7, so I'll put that on top, negative 7, over my change in x, which was plus 5, so over positive 5. So my slope for that one would be negative 7 over 5. Okay, moving on. Okay, some more examples. Another table, right? So we can practice that. I take a look at my change in x, which was plus 1. I take a look at my change in y, which was plus 2, right? Because 6 to 8 is going up 2. So my slope would be my change in y over my change in x, which would be 2 over 1. Okay, anytime you have a fraction of something over 1, it's just understood that it's that whole integer on top, right? So in this case, it would just be 2. So my slope would be 2. On a graph, this is where we can use rise over run. Rise over run. Okay, we can still use our slope formula if we wanted to because we have 2 points given to us, right? So we could still do, let's do pink, y2 minus y1 over x2 minus x1. Right, that's always an option. But on a graph, I tend to try to just do rise over run. Now, to do rise over run, okay, the number one thing you have to have, right, is you have to have 2 points. Have 2 points. Excuse my brilliant handwriting here. Okay, so in this case, I have this point here, which is at negative 3, 4, and this point here, which is at 2, negative 3. Okay, to do that, right, I'm going to take a look at my rise, which is my up and down. Okay, to go from this point to this point, I am going to go down 1, 2, 3, 4, 5, 6, 7. So I go down 7. So I'm going down, that would be negative 7. Okay, and then my run is left and right. So I'm going to go 1, 2, 3, 4, 5. Okay, because I'm going to the right, moving to the right is where all of my positive numbers are. So the value itself is also going to be positive. So I'm going to have -7 over +5. And that would end up being my slope. I don't need to simplify that because I can't simplify it. If I could simplify it, I would. Like if it was 4 over 2, you would simplify it down to be just 2. Or if it was 8 over 6, you could simplify that to be 4 over 3. Okay, so let's talk about some special cases. Given these points, right, we're still going to use our slope formula, right, which was y2 minus y1 over x2 minus x1. If you haven't noticed yet, I say this a lot, okay? If I repeat it a bunch of times, it's going to be super important, I promise, okay? So the slope formula, y2 minus y1 over x2 minus x1. So let's label our points, right? We've got x1, y1, then x2, y2. Okay, from there, we're just going to plug those values into our formula. So y2 is -2 minus y1, which is -2, over x2, which is 0, minus x1, which is -4. Okay, both these negatives get distributed. Okay, so they become positive. So -2 plus 2 gives me 0, divided by 0. This negative gets distributed there, so that becomes positive. So 0 over 4, right? So then I just have to think, okay, how many times can I divide 0 by 4? Okay, if you took 0 and you split it into 4 pieces, okay, how many would you have? Which would still be 0, okay? So 0 divided by anything is 0. Okay, we'll talk about what this looks like on a graph here in a little bit. So this would be if I have a slope of 0. We take a look at my values, right? My x values, I've got -4 and 0. Those are different. But my y values, -2 and -2, are the same. So when my y values are the same, my slope is 0. Let's take a look at this one over here. Okay, we've got x1. I want that to be red, please. x1, y1, and then x2, y2. All right, so y2 is 7, y1 is 3, so 7 minus 3 over x2, which is 6, minus x1, which is 6. Okay, 7 minus 3 is 4. 6 minus 6 is 0. Okay, so 4 divided by 0 is actually impossible. It's like one of the #1 major rules of math is you cannot actually divide by 0. If you do it, it's going to break space-time continuum. It's just impossible. Okay, if you were to do it in your calculator in front of you, it would bring up an error. Okay, it wouldn't even allow you to do the division. And now what that's going to be is undefined slope. Undefined. Because it is impossible, it is undefined. If I take a look back at my x and y values, right, what do we notice about our x's? When my x's are exactly the same, I have an undefined slope. When my y's were the same, I would have a 0 slope. Okay, so those are the two main special cases we talk about when we're talking about slope and rate of change. Okay, and we use this kind of mnemonic device to help us remember this. It just kind of sounds funny, so it always stuck in my head. HOI VUX. Okay, it's these acronyms to help us remember 0 and undefined slope. HOI stands for horizontal, right? Horizontal is left and right. Kind of like the horizon, right? Horizontal is like the horizon. If you have a horizontal line, that means I'm going to have a slope of 0. and it's always going to be y equals a number. Let me write number in here. Okay, there's not going to be an x anywhere in my equation. Okay, and it'll look like this example here. Vux, hoi vux. Vux stands for vertical, right? Vertical is up and down. If you ever forget which way vertical goes, I always try to talk about, when basketball players measure how high they can jump, they call that their vertical jump. So that's the connection I always made. When you have a vertical line, the slope is going to be undefined, okay? And it's always going to be x equals a number. Okay, it won't have a y in the equation at all. So like, for example, here on these examples, right, it's a horizontal line. This line would be y equals 3. Here on this one, it's a vertical line that passes through -6. So this would be x equals -6. Okay, and these are our special cases when it comes to slope. We've got positive slope, negative slope, zero slope, and undefined slope. Okay, so what if we know the slope, but we are missing one of the coordinates, and we have to find one of the coordinates? Here's how we would do that, okay? So they would give us one of the points, and then we got to figure out, okay, what is this over here, and then my slope is this. What you can do is set up a function, because or not a function, but an equation, right? Because we know y2 minus y1 is equal to x2 minus x1. So we can still take these points, right? If we got x1, y1, and x2, y2. Okay, I can plug in what I know. So y2 is r, y1 is 4. So r minus 4 is over x2, which is -5, and minus 1. Okay, -5 minus 1 will give me -6. So I've got r minus 4 over -6. Now my slope is 1/3. So it's equal to 1/3. Okay, and the easiest way to do this, which you might have heard of before, is to cross multiply. Okay, I'm going to multiply this times this. So -6 times 1, which will give me -6, equals 3 times r minus 4. Okay, and from there, right, you can distribute this 3 to both things. Okay, and we'll end up with, let me type it out so it goes a little bit faster. We'll end up with -6 equals 3r minus 12. Okay, from there we can solve the problem. We can add 12 to both sides. Add 12, so we get +6 equals 3r. Divide by 3, divide by 3. We would get r is equal to 2. If r is equal to 2, we can simply plug this back into the point, and we've got our point -5, 2. So that's how we can find our missing point if we know our slope and we're given a part of another point as well. Okay, little helpful hint here, right? We talk about it as like sort of like a ski slope. Okay, lines that have a positive slope go from the lower left up to the upper right, right? They go uphill as we're going up the hill. Negative slopes, okay, decline going from the upper left to the bottom right. I just realized I'm completely flipped for you guys, right? So it'd be from the upper left to the bottom right. Okay, lines that are horizontal, right, hoi vux, have a slope of 0. There's no rise. There's no numerator, or 0 as a numerator. If you're skiing, right, and you're on a flat hill, you're having zero fun. Okay. And if there is no slope, it is a undefined slope, right? There's no run to create that. If you have no slope, you have no shot of stopping your ski, right? So going up the hill, you have a positive attitude. Going down the hill, it could be negative if you're going too fast, right? If you're on a flat surface, it's zero fun. And then if you have an undefined slope, it's like you fell off the cliff, you're having no fun, right? No fun, no slope, or undefined slope. Okay? So what is the definition of a linear function? We've talked about it a little bit, but let's talk about what is the definition and then how do you tell if a table is linear, okay? A linear function is exactly what it sounds like. Linear is just a way to describe something that makes a line, okay? So it's going to create a straight line. The slope is constant, and constant just means the same. So it's the same over and over and over again, right? It won't be 2 at one point and then 4 at another point. It's always going to be the same. The slope is constant for a function when the rate of change is the same between any pair of points on the table of values. It creates a ratio that is exactly the same. So looking at this table, right, if I take a look at my x values, right, from 1 to 4 is going up 3, 4 to 7 plus 3, 7 to 10 plus 3, and 10 to 13 also plus 3. Okay, so far so good on my x values. I want to do the same thing for my y values, right? Minus 2, minus 2, minus 2, and also minus 2, right? Okay, so that one's going down 2. So my slope for this table, like we talked about earlier, would be negative 2, your change in y, over your change in x. So my slope there would be negative 2 over 3. That would be linear, right? Because the rate of change is constant and the ratio is the same between each of them. Okay, looking at this one, from negative 3 to 1 is plus 2. From negative 1 to 1 is 2, 2, and 2. On this side, you've got 2, 4, 2, and 4. So if you take a look at our y values here, it is not a constant rate of change, right? So this would be linear over here. Linear. Okay. This one on this side, number 8, would not be linear. So non-linear, NL. Okay. And the reason being, once again, right, it's going up by 2 here, but then by 4 here, right? And our ratio doesn't remain the same. Here, our ratio is 2 over 2, which is 1. But for these, it's 4 over 2, which would be 2. So my slope, my rate of change, is not constant. Therefore, it is not linear. Okay? So let's take a look at these final few examples, and then we'll wrap it up. All right? So this table represents a linear function. Find the rate of change and explain its meaning, right? So part of what you're going to have to do is look at the table and determine, okay, what is this really saying? So we've got a number of computer games and the total cost, right? So we can take a look at my change here. It's going up by 2, and here is going up by 2. Then we take a look here. Okay, we could do 156 minus 78 to determine our change, right? What happened from here to here, right? This becomes 16. This becomes 4. 4 minus 2 is 2. Right? Yes. Perfect. So. Oh, that's not a 2. Dummy me. That's a 7. I just can't write. So let's rewrite that. I'm like, wait a second. Doesn't make any sense. Okay, so let's have better handwriting, Coach Perkins. So 158 minus 156 minus 78. This still becomes 16. 16 minus 8 is 8. This has to become 14. 14 minus that is 78. Okay, so our difference here is 78. If I take a look here, our difference here is also 78. Okay, so for my ratio, I'd have to do 78 over 2. Turn that back on. Okay, I'd have to do 78 over 2, which comes out to be what? That's 39? Yeah. Okay, so my slope is 39. And then in the context of the problem, that's going to mean that your games cost $39 each. I can't spell. Dollars each. Make that a little longer. Cool. So let's take a look at, I think there's one more, or a couple more real life examples, okay? We have our number of floor tiles, right? Each time here is going up by 3. Over here, from 48 to 96 is a difference of 48. Okay, and from 96 to 44 is also a difference of 48. So my slope is our change in y over our change in x. So 48 over 3. Okay, 48 over 3 ends up being 16. So my slope is 16, which means that my floor tiles will cost $16 per tile. Okay, so then once you figure that out, you can determine, oh, cool, how much would it cost for 10 tiles? And you can do 16 times 10 and figure it out that way as well. Okay, and that ends up being our full example for slope and rate of change. If you're ever stuck or you need to go back and look at anything, be our guest. We're also going to post the completed hand notes after this, both my example and a handwritten example, so it's a little bit more clear, as well as some additional material to help you guys understand slope a little bit better. I will see you guys at Unit 3.2.